Okay, good afternoon, ladies and gentlemen. I hope you have your notes in front of you. I'm going to go through the notes and I'm going to treat them. And if you have a question or there's something unclear in the notes, make me aware of that and I'll try to explain. Okay, so let's open the notes. I'm going to page 2, and there on page 2 is the table of contents. So we're going to do 2 chapters in the textbook, chapter 3 and chapter 4. Now, chapter 3, let's look at those bullets. We're going to look at random variables, then probability distributions for discrete random variables. Third bullet, expected values of discrete random variables, moment generating functions, the binomial probability distribution, and the Poisson distribution. So that is chapter 3. Now, chapter 3 deals with discrete random variables, and chapter 4 deals with continuous random variables. In a moment, we'll see what a random variable is. Okay, let's go to the next page, page 3. Right, okay, that's just random variables. Next page, page 4, there's the introduction. Now, I know you can read that introduction, but nevertheless, let me read it. And if there's something to comment on, I will say so. Okay. If you are performing an experiment, and in that experiment, the outcomes is qualitative or quantitative, we use statistical analysis and to describe those experiments. Now, in those experiments that we perform, the concept of a random variable, that is something very handy. That allows us to go from an experiment to the real numbers. In other words, you allocate to your experiment that you have done, you allocate some real values, and that allows you to say something. Okay, and then in the half of that page, it says, okay, we'll focus on discrete variables, random variables, and in chapter 4 on continuous random variables. Okay, so now let's look at random variables. In any experiment, numerous characteristics can be observed or measured. But in most cases, an experiment will focus on some specific aspect or aspects of a sample. For example, in a study of commuting patterns in an area, I mean, you can imagine you've got some people at a bus stop that are waiting for the bus. And they say there are 20 people at the bus stop, and you are interested in the distance each of them has to travel. You see, so for those 20 people, you'll get different values depending on how far they travel. Or you may be interested in something else. On the next page, as I said, the distance that the passengers travel, the commuting distance, or you may be interested in the number of people commuting in the same vehicle. For instance, today on the bus at 8 o'clock, 20 people board the bus. Tomorrow, only 15, and so on. So you may be interested in many things. Now, on that page, in general, each outcome of an experiment can be associated with a number by specifying a rule of association. Now, such a rule of association, that is what we call a random variable. Now, if you look at that figure 3.1, you've got a rectangle there and it is denoted by S. So that is your sample space. So that means you've got some experiment that you are performing, and in that you've got some events in that sample that is relevant to your experiment. And now you have a function defined on those events, and the values of the function is on the real line. Okay, so that, loosely speaking, is a random variable. Now let's, on the next page, on page 6, let's see exactly what a random variable is. There is the definition of a random variable. For a given sample space S of the sample space S of some experiment, a random variable, we're going to abbreviate it RV, is any rule that associate a number with each outcome in S. But that is still very vague. Let's look at the definition of a random variable mathematically. A random variable is a function. The domain of the function is your sample space, the domain, and the range of your function is the real numbers. You see, so any function defined on a sample space with values in the real numbers, that is a random variable. Now, following that definition, it says random variables, we will denote them by uppercase letters such as capital X, that's a random variable, or capital Y, and so on. If you use a small letter x or a small letter y, that means that is the value of some outcome in your sample space of the random variable. So small x and small y, those are real numbers. Now let's look at a concrete example to illustrate all this. Example 3.1. Now the experiment goes as follows. When a student attempts to connect to a university computer system, either there's a failure or there is a success. Now you can see him, he's in front of his computer and he tries to connect. Either it is successful or it is a failure. So your sample space S consists of two outcomes, a capital S for success or a capital F for failure. And now you can define a random variable capital X as follows. Capital X at a point S, now remember S is one of the outcomes in your sample space. Capital X of S, you say that is 1, and capital X of F is equal to 0. So that random variable X assumes only two values, namely 1 and 0. Okay. Let's look at another example. Example 3 there on page, example 3.2 on page 7. Consider the experiment in which a telephone number in a certain area code is dialed using a random number dialer. So you've got a little machine in front of you. You press the button and the machine generates a telephone number. Okay? Right, now you can define a random variable capital Y as follows. You say Y is equal to 1 if that number that the machine generated, if that is a listed number, if that is an unlisted number. In other words, you've got a telephone directory and the number that the machine generated is not there in the directory, so then you will say Y is equal to 1. And Y will be equal to 0 if that number that the machine generated is in the directory. Okay, for example, if you have a number 5282966, if that number is in the directory, then y, my function of that point, will be equal to 0 according to your arrangement. Okay. Okay, so he says at the bottom of that example, in examples 3.1 and 3.2, the only possible values of the random variables, yes, with 0 and 1. Such a random variable arises naturally or frequently enough to be given a special name. We will come to that later on. Okay, let's go to page 8. There's a definition on top of page 8. It says any random variable whose only possible values are 0 and 1. That is called a Bernoulli random variable. It's just a special name. So if the random variable only assumes two values, 0 and 1, you call it a Bernoulli random variable. Okay, let's look at example 3.3. I think in the previous semester we had that one. Let's just read it. He says example 2.3 described an experiment in which the number of pumps in use at each of two gas stations was determined. Okay, so you are driving in a road and at the robot you stop. If you look to the left, there's a petrol station. There are 6 pumps there. If you look to the right, there's another station and there are also some pumps there, also 6. Right, now you let capital X be equal to the total number of pumps in use at the two stations. Okay, so you're going to describe this experiment as follows. If you stop at the robot, you write down a two-tuple. The first coordinate will be if you look to the left and then you count the number of pumps in use there. In the second coordinate, you write down the number of pumps if you look to the right. Okay. Now, capital Y will be the difference between the number of pumps in use at station 1 and 2, and capital U will be the maximum of the numbers of the pumps in use at the two stations. Okay, now if you consider a two-tuple with first coordinate 2 and second coordinate 3, that means the station 1 at the left, 2 pumps are in use if you look, and if you look to the right, 3 pumps are in use at the station on the right. So capital X of the two-tuple 2, 3 will be 2 plus 3, that is equal to 5, because that is how we define capital X. We said capital X is the total number of pumps in use at the two stations. Now, if you calculate capital Y of the two-tuple 2, 3, you're going to get Y is equal at the point 2, 3 will be equal to 2 minus 3, the difference, and that is equal to -1. If you look at your variable capital U, U is the maximum. So if you apply U to the two-tuple 2, 3, the first coordinate is 2, the second one is 3. What is the maximum? The maximum of 2, 3 will be 3. Okay, so there you also have some random variables and some experiment that you performed. Let's go to page 9. There's still another example, 3.4. Okay, that also comes from semester, second semester. And the experiment was this. You are sitting on a chair and you've got a basket in front of you, and the basket is filled with batteries that had just been manufactured somewhere. And now you conduct the following experiment. You pick up a battery and you test it. If the battery is good, you say it is a success. If you pick up a battery and there's something wrong, you say you get a failure. But the experiment works like this. You stop as soon as you get a battery that is working. So if I pick up a battery and I test it and it is working, that is a success, and then the experiment stops. Okay, that's one possibility. But you sit in front of the basket, you start over again, you pick up a battery, you test it, and it's a faulty battery, so then you're not finished. So then you pick up another battery and, okay, say that is a success, and then you stop. That's a second possibility. A third possibility goes like this. You pick up the first one, it is faulty. Pick up a second one, there's a fault with that also. So then you continue. You pick up another battery and you get one that is working. It is a success, and you stop. Right, now you can see in the second line, second and third line, the sample space S of that experiment looks like this. It's a set. You get an S or FS or FFS and so on. Now let capital X be equal to the number of batteries examined before the experiment terminates. So X tells you how many batteries you tested before the experiment terminates. Now, if you calculate capital X of S, so that means I picked up a battery and it was fine. So then I only examined one battery, so then X at the point S is equal to 1. If you calculate X at Fs, that means you examine two batteries, you'll get capital X at that point is equal to 2. And likewise, X at the point FFS will be equal to 3 because you examine 3 batteries. And so you can go on. Can you see that there is still another experiment and you defined a random variable? Okay, I think our final example is 3.5, and this is a different random variable. Let's see why. Now it says, suppose that in some random fashion, a location, latitude and longitude in the continent of the USA is selected. Now, okay, imagine you're sitting at some desk and the map of the US is in front of you. You take your pencil and you put it at a random point on the US. Now, at that point, you've got a latitude coordinate and you've got a longitude coordinate. Now, he says, for example, if the selected location were 39 degrees 50 minutes north and 98 degrees 35 minutes west, and at that point, the height above sea level is 1748.26 feet. So you've got a random variable. You apply that variable to the coordinates of your point, and that variable measures the height above sea level. Now it says, it is given to you that the largest possible value of y is 14,494 feet. And the smallest possible value of y is minus 282 feet below sea level. And he says that happens in the Death Valley. Now, this random variable is different from the previous ones. Let's just see why. He says the continuation of that example, the set of all possible values of capital Y is the set of all numbers in the interval negative 282. So the values are points Y is a number, and Y is bigger or equal to negative 282, but Y is also less than less than 14494. So your variable lies in that interval. So you must observe now there are infinitely many possibilities for your random variable y, and that type of random variable. This one is a continuous one. Okay. Now, you will make that more precise in the definition following all this. Two types of random variables. Okay, the definition says a discrete random variable is a random variable whose possible values either is a finite set, or if it's not a finite set, it can be an infinite set, but that range is actually a sequence. You can say there's a first value, second one, third, fourth, fifth, and so on. So, but you continue. There may be infinitely many, but you can say this is the first one, that's the second one, and so on. Right. That is a discrete random variable. Now he says a random variable is a continuous random variable if both the following two conditions apply. The set of possible values consists either of all numbers in a single interval. Now, if you have an interval, you know there are infinitely many points in an interval. And the interval may extend from negative infinity to infinity. But it can also be a union of intervals. For instance, the closed interval 0, 10, union the interval 20, 30. So if your random variable has values in, it's either an interval or a union of intervals, then you will say it is a continuous random variable. But now for a continuous random variable, if capital X, that second point, if your random variable X is continuous and you want to calculate the probability that that continuous random variable assumes a single value, C, then it is naught. It is 0. So you must remember, if you have a continuous random variable and you want to calculate the probability that it takes on a specific value, then it is 0. So if I get back to that one of, if I take my pencil and put it on the map of the US and I have a certain point, and I can then say, okay, the probability that this point has height above sea level, say 50 feet, that will be 0, you see. So a continuous random variable, if you want to calculate the probability that that happens, that's always 0. Okay, I see there's example 3.6. Let's read it. He says all the examples, all the random variables in example 3.1 through to 3.4, those random variables were discrete. Yeah, there's another one. Yeah, you can read that one. It's also a discrete random variable. Okay, that's all. Okay, ladies and gentlemen, I haven't seen any hands, but if you have something to ask me, you must ask me. Yes? Yes, Shibambo?
Sir, will you explain practical one?
Practical one. Okay. Well, just give me a minute. I must just open my notes to get that practical one. Okay, just give me a minute and I'll get back to you. Okay. Right. Okay, practicals. Where's prac one? Okay. Right. Okay, let me just get practical one. Okay. Yeah, my practical one on that sheet, it says it is practical 6. Are you with me?
Yes, yes.
Okay. Now, you can see there's an example explaining to you that now what you must do in that example, you can see there's a value x and a value f of x. Can you see that? X takes on the value 0, 1, 2, 3, 4, 5. And at each point, you calculate f of x and you get 0 0.1, 0 0.2, and so on. Now, what you can do is uh, you can multiply the x value and the fx value, and you can do that in every row. And so you can add a third column to that, and then you can sum everything in the third column. And the instruction that you do that is you use the sum product function. You see, and he explains to you to use it. Now let's look at that um, uh, question. He says, compute the probability that x lies between 1 and 4. Can you see that? The probability that x is greater or equal to 1 and less or equal to 4. Okay, so now you look at your table, the x values, uh, you can find 1, 2, 3, 4. So x lies between 1 and 4, but 1 is included, then 2 and 3. And the values on the right of 1, 2, 3, and 4, those are the probabilities, you see? And he says to calculate that probability, then you use the function prop, it stands for probability. Now, in the left-hand column, you will use the value 1, that is at the point A2, and you go, all the values go from 0 to 5. That is your, the left-hand range is from A2 to A7, and your B range goes from B2, that is 0.1, up to 0.1, that is B7. But you are interested only in the values 1 and 4. You see on the left, you are only interested in that. And then if you use that prop function and you put in those values, then you get the exact probability. So in other words, I'm going to add 0.2 plus 0.3 plus 0.1 plus 0.2, and that gives you the answer of the first one. Okay, and for the second one, the same thing happens. I mean, let's look at that second question. Now you calculate the probability that x is greater than 1, but less or equal to 4. Okay, so you go to your table, you identify the point 1, but you are only interested in the point 2, the point 3, and the point 4. And to the right of them, those are the probabilities, okay? So if I now punch my function prop, I again look at the left-hand column. The total range is from A2 up to A7. The second column, the probabilities, are also from B2 to B7, but now I'm only interested in 2 up to 4. And if you press that, then you will get the probability. So that is the second question, but it is very similar to the first question. Now for the C question, find the expected value of x. Okay, now in section 3.2, actually, we will get to the expected value, but what you must do now is you must take the left-hand value, you must multiply it by the fx value, and you add all those. And for that, you use the sum product formula. Can you see what I'm doing? I'm taking the left-hand value, the x values, I multiply the first one 0 times 0.1. I put that in a column next to it. Then the second value is 1. I times it by 0.2. I get the answer, put that next to that. And I do that for the whole column. And then I add all those values in the new column. But you can do that all simultaneously, you see. He says that is the expected value, but you use the sum product formula. Now, sum product works like this. You start from A2, the value 0, up to the value 5, which is A7. Then in the B column, I go from 2 to 7. Okay, that's all that you need. And you just press that, and it will calculate the expected value. Okay, now there's another exercise, and in that exercise, you do exactly the same as what you did in that example. Is it clearer for you, sir?
Yes, it's very clear.
Look, if you still struggle with it, in the next section, 3.2, in the theory, we are going to do expected values. You will see that, the definition, the formal definition of that. And if you have done that, then you get back to this, and then you can see this is just to let a computer calculate what you learn in theory. You will see that. Okay. Are there any more questions? Yes, Patel?
So with regards with tomorrow's tutorial test, would it be based on
Yes.
just chapter 3.1? Because the tutorial test that you uploaded for question 3 till 4, that's chapter 2 work. So I'm not so sure.
Say again, the tutorial test.
Yes.
Look, the tutorial test, look, let me now think of the test. If it covers it will mainly cover 3.1. Look, it's a 5-point test. It's short. It'll take you 5 minutes actually to do it. It's short, but my intention is that the work is from 3.1, but I may also look at work of 3.2, but it will be very basic. But let me just think
Thank you,
of
sir.
that test. Let me just think quickly. What did I ask? I have forgotten actually. In future, I will try to cover the previous week's work, if I didn't do it. But that is my intention.
Okay, thank you, sir.
Okay. Yes, Mr. Zwane.
So with regards towards the Blackboard link, this Ultra link, this session, it's only
Yeah.
available on mobile devices. I can't see it on my computer anywhere. So I was just hoping you would look at that, sir.
Is it not on your computer?
No,
that's
it's not on the
impossible,
computer.
man. I mean, look, I'm working from my computer. Are you registered for the course?
Yes, I'm registered for the course. So even the other students, so they say they can't find it on their computers too.
No, but there's not a link. I mean, if you go into the courses menu, there is on the left a menu item. It says Blackboard Collaborate Ultra. If you click on that, then the session is there, and you just click on the session and you are in.
Okay, sir, can I just show you real quick with my camera?
Okay. Okay, there are the menus. What happens if you click on the Blackboard Collaborate Ultra?
There is
If you
no
click,
Blackboard Collaborate Ultra, sir. It's
is
only
there not
a link
in the
no, there
menus?
isn't, sir.
Okay, I will inquire about that and find out why is that menu not there. Okay, I will
Yes.
definitely do it.
Thank you, sir.
Okay, okay. Okay, thank you.